Hey, it's Mr. Shrum, and we're picking up where we left off on the magnetic induction tutorial, and we were just getting into changing magnetic fields. Changing magnetic fields. So last time in this lesson, we've seen a change in a magnetic field can produce an electric current in a nearby conductor. Faraday discovered that magnetic induction can occur between two coils of wire that are separated by and wrapped around an iron core. As an increasing current is established in the first coil, the iron becomes magnetized. You'll sometimes see the term magnetic flux. Magnetic flux refers to the magnetic field strength B times the area through which that field passes. So as the voltage increases in a coil, so does the magnetic field and the magnetic flux that it produces. This increasing magnetic flux causes electrons in the second coil to move around in the opposite direction of the force from the magnetic field. The induced magnetic field inside any loop of wire always acts to keep the magnetic flux, magnetic field times the area of the loop constant. This fact is described by Lenz's law, which states that the direction of the induced current is such that the magnetic field resulting from the induced current opposes the change in the field that caused the induced current. As the magnetic field increases in strength, so does the EMF produced. This concept can be illustrated through the equation EMF equals BLV, since the EMF is directly proportional to the magnetic field strength. Transformers. Electrical power is something most of us take for granted. I know a lot of us did the past couple of weeks with the winter storm. Electricity runs our most basic devices. You might have noticed large metal boxes attached to electrical poles. Each box holds a device called a transformer. The electric company sends a high voltage current through the power lines, which stretch from pole to pole. This voltage is too high for most household appliances. The high voltage electricity must be transformed into a voltage that is safe for household appliances. So that's why we call those transformers, because they transform the voltage electricity. A transformer is a device that can raise or lower the voltage of the alternating current, AC, that passes through it. It's a really good example of Faraday's experiments put to use in everyday life. Transformers are found in stereos, refrigerators, air conditioners, and many other electrical devices. Let's take a look at how a transformer uses magnetic induction to raise or lower voltage. A transformer is made up of two coils of wires. These coils are kept separate from each other by insulation. However, they're both wrapped around an iron core. One coil is the primary coil, the other is the secondary coil. The primary coil is connected to a source of AC voltage. It's important that it be connected to AC in order to change the electrical field passing through. When turned on, the alternating current will create a changing magnetic field in the iron core. This changing magnetic field then produces an induced EMF and an alternating current in the secondary coil. This induced voltage, called the secondary voltage, depends on a few factors. First, it is proportional to the primary voltage being supplied. Second, it depends on the number of turns in the secondary coil and on the number of turns in the primary coil. The most common types of transformers are step-up and step-down transformers. The large transformer box connected to an electrical pole is an example of a step-down transformer. This transformer's secondary voltage is lower than its primary voltage. So what's coming into it is higher than what is going out of it. These transformers take voltages as high as 2400 volts and convert them down to usable levels of 240 volts. To do so, typically more turns occur in the primary coil than in the secondary coil. So you see how the primary coil is dealing with larger voltages. It needs more turns wrapped around the core. And then the secondary has less overall. On the other hand, a step-up transformer is the opposite. The primary voltage is lower than the secondary voltage. Once the electricity enters a house, there may be some devices, such as refrigerators, that require a larger voltage. In this step-up transformer, more turns occur in the secondary coil than in the primary coil. This process is shown in this illustration. This video is about Michael Faraday and his early experiments and discoveries. Once you are done, click next to answer a question based on what you observed. So let me play it here.
Some of the most important discoveries.
Let me see. Okay, so that should share the sound now.
Discoveries in electricity were made by British scientist Michael Faraday. Adam Hart Davies picks up the story of Faraday's groundbreaking experiments.
Faraday was fascinated by these results of Oersted's, and he was very keen to find out the connection between electricity and magnetism. So here in this very room, he set up an experiment, and I've got a recreation of it here. Powered with his voltaic pile, he made a little pool of mercury round a magnet in the centre there. And then he put a voltage between that mercury and this brass stand here. And he hung a wire. This is just a copper wire, which is going to hang from there in the pool of mercury beside the magnet. And just see what happens. Hang it in, complete the circuit. And it goes round and round and round.
Yeah.
So in this...
Pretty cool. I'll skip ahead because I don't want to play the whole thing. Might get copyright stricken. But it just goes on to say...
The magnet was moved inside a coil of copper wire. A tiny electric current flows through the wire. You can see the principle at work here. The movement of the magnet in between the two coils produces enough electricity to power a light bulb.
So yeah. What device is British scientist Michael Faraday credited with inventing? Well, he created the electric motor. Now it's your turn to perform a few experiments similar to those conducted by Michael Faraday. So we have this lab simulation, and I think I'll go through this next time after the lesson. If you want to increase the current of the secondary coil in an electromagnet, which of the following actions should you take? Well, if you want to increase the current, you would increase the number of loops in the secondary coil. As you've seen, magnetic induction can be produced with two coils of wire separated by an iron core. It is also possible to replace the first coil with a rotating bar magnet, which will still cause the second coil to generate power. This is the operational basis of electric turbines, whether powered by steam at a power plant, water at a hydroelectric dam, or wind in a wind turbine. Click here to learn more about how electric turbines work. We can look at that later. Another practical application of magnetic induction is found in cooking. Instead of a gas or an electric burner, cooks can use an induction cooktop. This special cooktop has coils located just below the surface that carry an alternating current, which in turn creates a changing magnetic field. This type of cooking requires special cookware in order to heat food. These pots and pans are called ferromagnetic cookware because they are rich in iron. When this equipment is placed in the magnetic field, it acts as a conductor. A current is induced on it. That current is converted to heat inside the ferromagnetic cookware to cook the food. And in that type of cooking, the cookware and the food inside it gets hot, but the cooktop itself does not get hot. So finally, in summary, Michael Faraday made many important contributions to the field of physics, especially in the area of magnetic induction. Oersted's work with electric and magnetic fields led Faraday to experiment and test his hypothesis that magnetic fields can produce electric fields. His discovery of magnetic induction demonstrated that electric current could be produced from a changing magnetic field. In the most common case of magnetic induction, two coils of wire are separated by an iron core. As an alternating electric current is sent through the primary coil, the iron core becomes magnetized. This in turn creates a voltage in the secondary coil, and thus the ability to generate an electrical current. There are many important applications of magnetic induction, for example, airport metal detectors, traffic light sensors, electric turbines, and of course, induction cooktops. The induced potential difference, or EMF, can be found using the equation EMF equals B times L times V, where B is the strength of the magnetic field, L is the length of the wire, V is the velocity of the wire moving perpendicular to the magnetic field, and multiple factors can affect this induced current. If the magnetic field increases, the EMF will also increase. If the magnetic field decreases, so will the EMF. Also, changing the number of loops in the wire can affect the EMF. The more loops, the greater the EMF. So next time you're in an airport, driving in your car, looking up at the transformers on your street, you will have a better understanding of how magnetic induction works in your everyday life. And that's that for magnetic induction. I'll go back and look at that lab with you. But until next time, have a great day, great week, and I will see you all next time. Bye-bye.